Hey everyone, welcome back to yet another episode of machine learning. Today we are doing a paper review that is landslide susceptibility modeling by interpretable neural network. I'm Magino Daniel. So let's dive in. Artificial neural networks initially were brought in with the concept of the neurons that work in the brain. So artificial neural networks in this project were used for landslide susceptibility, that is predicting the likelihood of landslides. They were accurate, but the only challenge was that they were largely uninterpretable, which brought about a computational problem. So the scientists got a solution for that. The solution was the supposable implementing of the supposable neural network that features in the full interpretability, the accuracy, and generalizing. So this is the structure for the traditional and the supposable neural network, as you can see. So we have our inputs here for the traditional neural network, which is a deep neural network. It is initially an example of artificial neural network. So we have our inputs here. We have these hidden layers that are interconnected with each other, as you can see, to give us an output here, that is Y. But generally, this concept here is a black box concept, which brings about the bias. That's why the deep neural network was not considered, since we are dealing with landslides, which are a problem. So the supposable neural network here have got inputs that are mapped onto a pair of the neurons. As you can see, we have here the pair of the neurons that are mapped onto each input. And then later on, we get the summation of these pairs of the neurons. And after that, we get the total summation that leads us to the total susceptibility or likelihood of landslides. So initially, supposable neural network is better. So this is the multivariate polynomial expansion, where we explore very many features. After exploring many features, we then choose or select the best in the tournament ranking. We choose the best features. Then a multi-stage is where we train the teacher neural network. After training it, its output is further used for training the student neural networks, as you can see in the fractional knowledge distillation. So the student neural networks sum up to give an output that is later on where later on we get the difference between the current target and the total output. So this is summed up. So then for the performance improved, if the performance did not improve, we then group the neural networks. As you can see, the layers, we group them according to the features they are working on, and later on we merge them to come up with a possible neural network. These are just the composite features, single and then the composite. Then this is the Eastern Himalaya map where the project is taking place. This is the Dibang region. This is the Front Range region. Then this is the Lohit region. These are the features of the data set. The link to the data set is there too. Then we have also the features. Actually, these are the features also for the data set, the 15 features illustrated. Then these are the correlations between the features, as you can see, where the one represents the positive correlation, the negative 0 will represent the negative correlation, and then 0 itself is in between the correlations. So we then go to the flowchart detailing the semi-automatic landslide mapping, where we have the 50 by 50. After getting the features of the images here from the manual landslide inventory, we then group them according to the landslides and no landslides. As you can see, we annotate them. Then after we still further use the image segmentation where we are able to come up with so we are able to prepare the patch as an input of the 32 times the 32, which then gives us the 12. This 12 stands for the sum of the 5 land set, and then the 7 features of the input. So then we use here the convolutional neural network to further map the region that has that's susceptible to landslides. Then we come up with a stitch, that is our output, and later on the experts will check for corrections on these stitches, and also amalgamate to check for areas that have been joined together, and yet they have different, and yet they are different. So the mapped landslides susceptibility. So here we have the A and D, which are the debug region. Then we have the B and E, which are the front range region. Then we have the C and F, which is the low heat region. So this region here, where you see the red, signifies the landslide areas, as you can see. And then this signifies the threshold here, as you can see, with the total susceptibility, as you can see. So initially in A, we have about 959 landslides. Then in B, we have about 1,536. Then for the case of C, we have 356 landslides. Then the thresholds here, for D, we have 0.767. Then for E, we have 0.861. Then for F, we have 0.816. So initially, that's it for this. Then for the data splitting, we use the mechanism known as the Pythagorean tiling, which uses the concept of Pythagoras theorem, where you calculate the squares of A, summing it with B, and then equating it to C squared. So this was used majorly for coming up with a checkbox-like pattern for partitioning the training data and the testing data. So the larger squares that are in green are the training, and then the small squares, as you see here, the small ones in green are the testing. This is 70%, this is 30%, as you can see. So yeah, initially this was used for the partitioning of the data because it's accurate and it does not bring about the bias in the data. So we then have the model evaluation metrics that we applied. These are the metrics used for evaluating these models, as you can see. And we see the area under receiver operation cover is the one that has got the highest metric, as you can see, because it's actually the best in having the good prediction. Sorry, in evaluating the model, because the models we have here, we have the multi-stage training here. We have the superposable neural network, the level 2 and the level 1, logistic regression and the likelihood regression. So yeah, initially the best metric here was the area under receiver operation cover. The rest are having some issues with for example, the accuracy. When it comes to imbalanced data sets, it's not accurate. Then for the true positives and false positives, these ones only concentrate on the positives. They don't concentrate on the negative sides. Then even for the positive and the probability of detection and probability of false detection, this also concentrates on the positives only and leave out the negatives, which really is necessary for evaluating the model. So yeah. Then we have this. These are the regions, the 3 regions. The first region, the second, and the third region. The first, which is the debug, followed by the front range and the low heat region. So as you can see, we have we have the features that are multiplied together. These are composite features. Wherever you see the multiplication, these are composite features, and the ones that are the ones that are not multiplied are the single features. So we have here the likelihood of landslides occurring at this point, and even here, as you can see, the likelihood ratio. So the likelihood ratio, if the likelihood ratio is equals to 1, then that is the average of that's the average of the susceptibility of landslides. Then if it is above 1, that means that's a high risk of that's the high risk of a landslide occurring, as you can see. So specifically, that is what I can then for the contributions to the total susceptibility, we have for the three regions again, as you can see, the debunk, the front range, and a low heat region. We have the bar graph and the pie chart. As you see, the pie chart here consists of the total susceptibility of landslides and the total susceptibilities of no landslides. As you can see, the averages are here. But then on the side of the bar graph, we have this symbol here that signifies that that signifies the difference between the areas with landslide and average areas of that have no landslide. So majorly, this is it. The bar chart was depicted from sorry, the pie chart was depicted from the bar chart, as you can see. So the important controls for the landslide, these are the things that signify. As you can see, we have the primary features. That's the primary features that are also still composite features, as you can see, because they are multiplied. So we have the areas of the slope that are having the color, they follow they correspond to the colors, as you can see. The map curve, the aspect and relief, the number of extreme rainfall events and slope, as you see. And then here also we have the climate, the climate that is in the blue, and then the slope that is in red. So these are the features that contribute to the likelihood of landslide. They are mapped here, but then there are areas that are in white, as you see. These are areas that were not mapped among the areas that have a landslide or do not have landslides. So yeah, basically the supposable neural network outperformed the physically based data-driven approaches and machine learning techniques. Where the physically based, these depend on the concept of physics, where they come up with an equation. Then for the data-driven, this basically concentrate on the past data to come up with a prediction. Then for these other metrics, yeah, they support a vector machine and the random forest. Then the model that tried to achieve the average performance with the supposable neural network was the state-of-art deep neural network. However much, the only challenge it has is a black box. It's based on a black box model whereby its processings are hidden and hard to understand. So that still makes supposable neural network the best. The strength of supposable neural networks, we have interpretability. It's very easy to interpret due to the Gaussian activation function that made it easy for the neurons to map to the inputs. And then the accuracy, it's accurate, as you can see, and it uses the metric of area under receiver operation characteristic. Then generalizability, it was used in 3 regions, as you recall, the low heat region, front range region, and the bang region. Then the weaknesses, we have data dependence, it relies on quantity of data and quality of data. If the data is not of quality, then you will have a weak prediction. Then for the computational demand, sorry, for the computational demand, identifying composite features for the SSN can be computationally intensive. So in conclusion, the SSN offers a promising approach for landslide susceptibility modeling by combining accurate predictions, which are valuable. Yeah, thank you so much for listening. Yeah.